In today's lesson, we are going to be looking at solving by elimination. So this is another method of trying to find the solution to a linear system. And it's similar in a sense to solving by substitution in that we aren't going to be graphing our lines. So this is one of those situations where graphing a line um, may not be easy, right? Probably because it's in a standard form, or doesn't convert nicely, or things like that, or maybe the solution isn't the nicest. So this is just another method. Now, this is going to differentiate a little bit from solving by substitution, and it could be an alternative to solving by substitution depending on what equations you're given. So what we're going to start with these steps. So we're going to look at the steps in general first, and then we're going to apply them to some different examples. So the first step, we want to decide which variable to eliminate. So when we're talking about the variables, remember we're talking about x or y, right? Those tend to be our two main ones, right? But it could be anything depending on what our variables that we're dealing with. Maybe it is a word problem or something like that. So we might have different variables, but we can think of it as being x or y. So we have to pick one of those variables to eliminate. And there are things that we can look for to help us choose which variable, but in the end, it doesn't really matter which one we pick. It just determines how easy or challenging the process is. Right? To eliminate a variable, though, it must have the same numerical coefficient in both equations. So if I want to eliminate x, the number in front of x has to be the exact same in both equations. Now, in some cases, the equations might already have the same numerical coefficient, and in other cases, we might have to change the equations to get the same numerical coefficient. All of that we'll look at in some of the examples, though, that we deal with. Once we determine the variable to eliminate, they have the same coefficient. To eliminate them, to do the actual elimination, we need to either add or subtract the equations based on the signs of the variable. Right? So whatever we're trying to subtract, or eliminate, whatever variable, if the signs are the same, we are going to subtract. So if they're two negatives or two positives, we are going to subtract the two equations. If the signs are different, we are going to add. So if the signs on the two coefficients are different, we are going to add positive and a negative in any sort of variation. We are going to subtract or add them. Once we do that, once the variable has been eliminated, we're going to continue to solve for the variables as we have previously. So similar to what we've done with solving by substitution, we're going to do the same thing. So the only difference in elimination is that we're using a different method to get rid of one of the variables. In substitution, we substituted. In elimination, we are going to eliminate one of them. So let's take a look. Right? So example 1, we want to solve using elimination, and then we're going to check our answer. Right? So we have 7x minus 4y equals 3 as one equation, and 6x plus 2y equals 8 as our second equation. Now, right now, both of these equations do not have a common coefficient in front of a variable, right? For the x's, we have 7 and 6. For the y's, we have negative 4 and positive 2. So what can we do? Right? Well, we can change an equation, right? And we can change an equation by doing something to every single term. And usually this means multiplying or dividing. One of those two scenarios. Think of changing a fraction to get an equivalent fraction. We could multiply or divide the numerator and denominator to get an equivalent fraction. Same idea with an equation. We can multiply or divide the entire equation to get something that is equivalent. So, for example, if I were to look at the variables x and y and say, okay, which coefficients could I get close to each other? And if I look at the y's, well, 4 and 2, those numbers are related by a multiplication or by a factor. So what I can do is I can take equation 2 and multiply by 2. So I'm going to do that first. I'm going to take equation 2 and multiply it by 2. Right? So you could write that out as a step, or you could just write out equation 2, and we're going to multiply that by 2. So I'm going to start with that. I'm going to write that, or I'm going to leave equation 1 on top because they haven't changed it. So 7x minus 4y equals 3. That's the first equation. We haven't done anything with it. The second equation that we multiplied by 2, I'm going to rewrite it with every term doubled or multiplied by 2. So 6x becomes 12x. Positive 2y becomes positive 4y. And 8 becomes 16. So now I've multiplied the second equation by 2, and now we have a common coefficient for y. So now I'm going to choose to eliminate y. So I've taken the first equation, I've multiplied it by 2. Now I'm going to eliminate y. So we're going to eliminate y, and we're going to do that by either adding or subtracting the two equations. So if I look at my two coefficients on y, one is negative, one is positive, our steps say when the signs are different, we are going to add the equations together. And when we add the equations together, what we can do now is collect like terms in a sense. And it's helpful to have our equations lined up like this so that we can see what we're focusing on. So the 7x plus 12x, that becomes 5, or not 5x, that becomes 19x. Negative 4y plus positive 4y becomes 0. Right, so we always use this outside operation as what we're doing overall. So 19x plus 0 equals 3 plus 16, which is 19. And that's exactly what we want. We want to have one of those variables get eliminated. We want to have 0 as one of those options because that means our variable is gone. Now that our variable is gone, we can start to solve our equation because we have 19x equals 19. I'm going to solve for x, divide both sides by 19. One side cancels out. Let me change that. And I'm left with x is equal to 1. So very similar to substitution, I have removed a variable, I have one variable left, and I've solved for that variable. What we're going to do next is now we're going to take that variable and we're going to plug it back into one of the equations and solve for our other missing variable. So I'm going to substitute x equals 1 into, and again, it doesn't matter which equation we use. Let's just pick equation 2 for the sake of argument. Again, it doesn't matter which one we plug it into. It should get us the same answer either way because it is, again, this point of intersection, this solution is a shared point or has shared coordinates between the two equations. So we have 6x plus 2y equals 8. I'm using the original equation just because it has smaller numbers. You could use the one that we changed back up here if you really wanted to. It should still give you the same answer. So 6x plus 2y equals 8. Instead of x, we're going to plug in 1. So 6 times 1, plus 2y equals 8. 6 times 1 is 6, plus 2y equals 8. And now I'm going to solve for y. I'm going to bring the 6 over. It becomes negative 6 or minus 6, so 2y equals 8 minus 6. 2y equals 2. I'm going to get y by itself by dividing both sides by 2. And I have y is equal to 1. This means then, therefore, the point of intersection is the point 1, 1. I can check this as well if I want. I don't have to worry about checking equation 2 essentially because I got this value from equation 2. So I can check equation 1 though. 7x minus 4y equals 3. So 7 times 1 minus 4, minus 4 times 1 equals 3. 7 minus 4 equals 3. 3 equals 3. That is good. For sake of argument, let's just check the second one. 6x plus 2y equals 8. 6 times 1 plus 2 times 1 equals 8. 6 plus 2 equals 8. 8 equals 8. That works as well. So again, similar to substitution, we can check our answer by plugging it back into both equations. And it should work out. Right? The left side should equal the right side. It should make sense, which in this case it does. Let's look at another example. Now with these two equations, again, we're trying to solve by elimination, but if I look at these two equations, there's nothing very nice about them, right? If I look at the variables, the coefficients in front of either variables or either variable is not the same, right? Between the x's and the y's, they're not the same, and I can't really get one to the other or one the same as the other by just doing something easy like the last one. So in this case, again, it's like trying to find a common or it's like trying to find an equivalent fraction between two fractions, or a common denominator between two fractions that don't kind of pair up nicely. So in this case, what we're going to have to do is we're going to have to change both equations, right? And the easiest way to do that is to pick a variable that we want to eliminate. So for example, let's get rid of y again. So if I want to get rid of y, we want to eliminate y, I need the coefficient in front of the y's to be the same. Right? So in order to do that, I'm going to take equation 1 and I'm going to multiply it by the coefficient in front of the variable I'm trying to eliminate in the other equation. So I'm going to multiply equation 1 by 3. Don't worry about the signs, we're just focusing on the number. I'm going to take equation 2 and multiply it by 4. The coefficient in front of the y value in the first equation. And that's going to give me two equations that are still equivalent to what we have here, and it's going to allow or cause the variable or the coefficients in front of the y variable to be the same. So for equation 1, right, multiply every value by 3, 8x becomes 24x minus, and then 4 times 3 is 12. 24x minus 12y equals 48, or 16 times 3. My second equation, 5x times 4, so I have 20x minus 12y, because 3 times 4 is 12, equals 44, or 11 times 4. Now that I've done this, now I need to figure out, okay, what am I going to do? I need to do something to eliminate the y values. So I have negative 12 and negative 12. How can I cancel those out or eliminate them? Well, I can add them, or sorry, not add them, I can subtract them, because negative 12 minus negative 12 is the same thing as saying negative 12 plus 12. And if we go back to our steps, if they have the same operation, we subtract. So I'm going to subtract these two equations. So 24x minus 20x is 4x. Negative 12 minus negative 12 is 0. And 48 minus 44 is 4. Now, when we're dealing with subtraction, if it helps, maybe put brackets around the second or the bottom equation, just so we know that we're subtracting everything, right? And we always kind of start with the term on top, go to the operation on the side, and then go into the term that we're subtracting or adding, whatever the case may be. So when I subtract these two equations, I cancel out my y variables, which is fine. I want one variable by itself, in this case x. So we get 4x equals 4, and I'm just going to go through and solve this equation for x. divide both sides by 4. One side cancels out. We're left with x equals 1. So now I know part of my point of intersection. I know the x value. And similar to what we did before, let me just keeping it color coded. What I did before, I'm going to sub x equals 1 back into any equation. Now it doesn't matter which one we want. We could plug it, or we could plug it back into equation 1 or back into equation 2. Just to keep things consistent with the other one, let's plug it into equation 2. But again, it shouldn't matter. So I have 5x minus 3y equals 11. Again, I'm using the original equations, which is fine because I don't want to deal with these inflated numbers, and it's going to give me the same answer either way. So 5 times 1 minus 3y equals 11. And now I'm going to go through and solve for y. So 5 times 1 is 5, minus 3y equals 11. Move the 5 over, it becomes subtraction. Negative 3y equals 11 minus 5. Negative 3y equals 6. Divide both sides by negative 3 to get y by itself. One side cancels out, and we have y equals negative 2. Now that we have those two pieces, therefore, the point of intersection is 1, negative 2. So with my point of intersection, if I want to double check my answers, I can, right? We can just take those values and plug them back into our original equations. So I'm going to check the first one. 8x minus 4y equals 16. 8 times 1 minus 4 times negative 2 equals 16. 8 minus negative 8 equals 16, and I get 16 equals 16, which is correct. Let's move this over and move most of it over. I'm going to check the other equation. 5x minus 3y equals 11. 5 times 1 minus 3 times negative 2 equals 11. 5 minus negative 6 equals 11. 11 equals 11, which is right. So I've checked my answer. This point of intersection is correct because it exists on both lines, so I know my answer is correct. Example 2, now we're dealing with linear equations in standard form that have fractions. So this is now complicated. It's messy. We don't like these types of questions, but they may come up because, again, it all depends on the type of equation that we're dealing with, and that's sometimes out of our control. Right, so one thing to note, when we're dealing with fractions, eliminate the fractions by multiplying by a common denominator. So we want to multiply by a common denominator, or depending on the fraction, just multiply each one by its denominator. Get rid of the fractions first and then worry about finding a common variable later. So what I'm going to do, I'm going to take equation 1 and I'm going to multiply it by 3. I want to multiply it by 3 because of this denominator here. That's the only fraction in that equation. In equation number 2, here is going to be a little bit different because I have two different fractions. I have 1 over 4 and 1 over 2. But luckily there's a common denominator between those two, which is 4. So now we're going to go through and multiply each of those equations. So equation 1 becomes, this. So equation 1 becomes 1/3 times the third is just 1. So 1x minus 27y equals 15. Equation 2 becomes, well, 1 over 4 times 4 is just 1x. And then negative 3y becomes negative 12y. And 1/2 times 4 becomes 2. So now I've changed both equations. And I've gotten rid of my fractions. What I can do now is I can eliminate, right? Because looking at this, I have the same coefficient in front of the x's. So I can eliminate the x's or solve this linear system by elimination. So I'm going to subtract these two, and because they're the same signs, I'm going to subtract. So 1x minus 1x becomes 0, negative 12y minus, and if it helps with the minus to put brackets, negative 27y minus negative 12 is the same thing as saying negative 27 plus 12 becomes negative 15y, and negative 15 minus 2 becomes 13. I'm going to solve for y. Right, because I just have negative 15y equals 13. Divide both sides by negative 15. One side cancels out. We have y is equal to negative 13 over 15. So not the nicest equation, right? Not the nicest value or coordinate for y, but it does allow us to see why it might be better off to solve by elimination than graphing, right? We might not be able to find this value accurately when we graph. Once we found the one value, we're going to substitute that back in. So we're going to substitute y equals negative 1 over 3, or negative 13 over 15 into either equation, right? Whichever one we want. I'm going to sub it into equation 2. And in this time, I'm going to use the new equation because there's less fractions to deal with. So I'm going to use 1x minus 12y equals 2, right? Which is fine to do because, again, it's equivalent to the equation, our original equation. So replace the y. So x minus 12 times negative 13 over 15 equals 2. Multiply our fractions, so I get x equals positive 52. No, not 52. I've reduced it already, so it becomes positive 52 over 5 equals 2. Move the 1 over to the other side. X equals 2 minus 52 over 5. We get x is equal to negative 42 over 5. You could use decimals. It's obviously not going to be as accurate as using the fractions, but it might be easier for you to work with. Just be careful with your rounding, right? Leave a few decimal places. A good rule of thumb is probably leave at least 2 decimal places, just to avoid any rounding errors. So we've solved for both values, so therefore the point of intersection is negative 42 over 5 and negative 13 over 15. Again, if we wanted to, we could check this answer by plugging it back in. If you do use decimals when it's going through and solving this, you might get approximately the same answer, or it might be close when you do left side equals right side. So you do have to be aware of that. If you're rounding when you check your answer, or if you check your answer, it might not be 100% correct or accurate. And then one word example or one word problem. So every day at her bakery, Brittany bakes chocolate chip cookies and oatmeal cookies. She uses different amounts of butter and oatmeal in each recipe. I don't know why there's oatmeal in both, but sure, maybe it's oatmeal chocolate chip. So each batch of chocolate chip cookies uses 13 kilograms of butter and 8 kilograms of oatmeal. While each batch, not back, each batch of oatmeal uses 2 kilograms of butter and 28 kilograms of oatmeal. If she has 47 kilograms of butter and 140 kilograms of oatmeal, how many batches of each type of cookie does she bake? So what we're looking for is batches of each type of cookie. So that will help us determine what our variables are going to be, right? Because we don't have any equations here, so we have to come up with our equations. So we're going to let B, or sorry, batches. So we're going to let C equal number of chocolate chip batches, and we'll say let don't really want to use O just because it's oatmeal or for oatmeal, and sometimes O might get confused with 0. So let's use A, just the second letter. Let A represent the number of oatmeal batches. So now that I have my two variables, I need to come up with two equations. So this is probably going to be the hardest part out of any word problem in this unit, is coming up with the equations. Right? So we have relationships, and we know total amounts. Right? So the idea is looking for total amounts is going to be helpful. Right? Because that tells me that something in our scenario has to equal this amount. And what we have is we have total amounts for butter and for oatmeal. So there's probably going to be some sort of a relationship between our variables and the total amount of butter used, and between the batches and the amount of oatmeal used. So let's look at butter. If I go back and look at butter, well, chocolate chip cookies use 13 kilograms of butter, and oatmeal cookies use 2 kilograms of butter. So I can come up with an equation for that, because if I know the number of batches, I'm going to for chocolate chip, I'm going to multiply that by 13 to tell me how much butter was used for the chocolate chip cookies. Same thing for the oatmeal cookies. 13 times C, and 2 times A for the oatmeal has to work out to 47, how much butter we used. For oatmeal in total, right, for oatmeal in the recipes, again, looking back at these scenarios, 8 kilograms of oatmeal for the chocolate chip cookies and 29 kilograms of oatmeal for the oatmeal cookies. So here it'd be 8C plus 29A equals 140. We now have our two equations. So looking at these two equations, there's not one that looks like it'd be nice to isolate for, so we don't really want to use substitution. Elimination is our best bet when we don't have a variable already by itself or with a coefficient of 1, but we don't have any coefficients that are the same. So what we're going to have to do is change these equations. So let's pick a variable to eliminate. I'm going to eliminate or try to cancel out A. Right? Smaller number in 2, right? So maybe I think the numbers are going to be smaller overall. You could try to do the same thing by eliminating C first, or getting the coefficients in front of C to be the same. It should work out to be the same either way. So I'm going to take equation 1 and equation 2. And if I look at A, use a different color here. If I look at A here, these terms, the numbers don't really relate nicely. And that's fine. It just means we're going to have to change both equations. And what we did in the similar example previously, we take equation 1 and we're going to multiply it by 29 because that is the coefficient in front of a in the second equation. For equation 2, we're going to multiply that by 2, which is the coefficient in front of a in the opposite equation. This now leaves us with two new equations. So if I take the first one and multiply it by 29, I get 377x plus 58m equals 1,363. My second equation, multiplying everything by 2, which is a little bit nicer, I get 16, not x, sorry, and not m, c and a. So I get 16c plus 58a equals 280. Now I have a common coefficient in front of a. So now I can eliminate my variable. I just need to figure out, do I add or subtract these two equations? Because the sign in front is the same, we're going to subtract. I'm going to put brackets around the bottom equation just to make sure we're on the same page, or we remember that we're subtracting everything in there. So 377 minus 16 is 361. 58 minus 58 is 0. And 1363 minus 280 is 1083. And now I'm going to go through and solve. So I get 361c equals 1083. I'm going to divide both sides by 361. One side is going to cancel out. I get c is equal to 3. So that means that there are 3 batches of chocolate chip cookies being made. I know part of my answer now. I just need to figure out how many oatmeal batches are being made. So to do that, I'm going to sub c equals 3 back into either one of my equations. I'm going to use equation 1 this time just because overall the numbers are smaller, so hopefully the less larger numbers makes it easier to calculate. Again, it doesn't really matter. So if I plug it in, I now have 13c plus 2a equals 47. 13 times 3 plus 2a equals 47. 39 plus 2a equals 47. 39 moves to the other side, it becomes subtraction. 2a equals 47 minus 39. 2a equals 8. One-step equation, we could just go through and calculate or do this in our head, or divide both sides by 2. One side cancels out, and we have a is equal to, looks like a 9. A is equal to 4. So that means that there are 4 batches of oatmeal cookies. So therefore, she bakes 3 batches of chocolate chip and 4 batches of oatmeal. So that's our last example, looking at solving by elimination. Again, the latter part of the process is very similar to solving by substitution, the idea of plugging a value back into one of the equations and solving for the other. The difference is, how do we find that variable or the value of a variable right off the bat or at the beginning? And in this case, we're trying to find a common coefficient for one of the variables. Then we're adding or subtracting the 2 equations to cancel it or eliminate it. Again, keep in mind, we might have to change the original equations to allow us to eliminate, but we've looked at examples with that. And then the latter, like I said before, the latter part is very similar to solving by substitution. So again, these are two methods, or this is another method to solving a linear system, finding the point of intersection, which might be more useful in some cases, depending on again what type of equations were given. Right. So as you practice it more and more, hopefully it becomes clear which scenarios are better suited for substitution or graphing or now elimination.